Let's say a car is driving 50 miles per hour and they keep it steady, exactly 50 miles per hour, and they do this for 2 hours. What could we determine from this situation? It's like, well, if you think about the situation, they're going 50 miles every hour, right? That's what miles per hour means. 50 miles every time an hour goes by. So if 2 miles go by, or 2 hours go by, well, then that's going to be 2 times 50. So that's going to be 100 miles. So I want to think about the math behind the units here and why this is. If you have a rate and you multiply it by a time, you end up with a distance, right? That's what we have here. The rate that something's traveling at, the time that it's traveling, and then finally how far the vehicle traveled over that interval. And here's the reason for why that is. Rate is measured in some amount of distance per some unit of time. So miles per hour, feet per second, yards per minute, whatever you're measuring, it's going to be a ratio of distance divided by time. So when you go and multiply by time, well, that time, if you think of that as a ratio or a fraction, that's just time over 1 here. So if I were to multiply these two things together, what would happen? Well, you've got miles divided by hours times hours divided by 1. So ultimately here you have miles times hours over hours. Those two things cancel each other out. Hours divided by hours is just going to leave you with 1. So you just end up with miles or distance. That's why this happens. So it's very important for us to remember this little formula, that rate times time equals distance. Now there are other parts of this that come from that discovery that are very important. So for example, you may want to make the note that if rate times time equals distance, well then there are other things that are going to follow from that as well. If I were to divide both sides by time, then I would end up with rate equals distance divided by time. That's also true. So if I wanted to know how fast I'm going, all I have to do is divide the distance I've traveled by the time that I've been traveling for, and that will solve for rate for me. Similarly, if I want to solve for time, all I need to do is divide the distance I've been traveling by the rate that I've been traveling at. So these three formulas are all true, and we're going to need to use them in these word problems that ultimately are going to turn into equations for us to solve. But the second part of this lesson is going to be interpreting word problems to help solve real-world situations. So the first problem says 2 cars left from the same spot and headed in opposite directions. So we got the spot, 1 car going that way, 1 car going that way. 1 car was traveling 10 miles per hour faster than the other car. So this is talking about rate. If I say that X is the rate of 1 car, then X plus 10 is the rate of car 2. All right, so one's going 10 miles per hour faster. After 3 hours, so 3 hours go by, the cars were 240 miles apart. How fast was each car traveling? There's a lot we know and a couple of things we don't know. So we're going to make a table. And we often make these tables based on the idea that rate times time is equal to distance. So I'm going to make a table that has 3 columns. And I only need 2 rows here. I've got car 1 and I've got car 2. So let's think about the things that we know. We're trying to figure out how fast each car was traveling, so it's good that our unknown is rate, right? We said let x equal the rate because that's the thing we're solving for. So car 1 has a rate of something, car 2 has a rate of something plus 10. Here's the other thing we know. After 3 hours, the cars are a certain distance apart. So 3 hours goes by for car 1 and 3 hours go by for car 2. Now the question is, if the cars are 240 miles apart, how fast was each car traveling? I do not want to put 240 in either of these two boxes, because by doing that, I'll be saying that car 1 traveled 240 miles and car 2 traveled 240 miles. I don't know how many miles car 1 traveled. It's going to be less than 240 because some of this is car 1 and some of this is car 2, but I don't know how much of it is each car. So what I'm going to do instead is I'm going to say, I know that rate times time equals distance, so if I take this rate and multiply it by this time, that gives me the distance that car 1 traveled. It's definitely 3 times x. Whatever the rate of car 1 is, multiply that by 3, that's how far car 1 went. Car 2 had to have gone this far, because whatever its rate was, multiply that by 3, that's the distance that that car traveled. So here's what we've got then. Car 1 traveling some distance, and car 2 traveling some distance, and together those add up to 240 miles. So I've got the distance traveled by car 1 plus the distance traveled by car 2, and together that has to add up to 240 miles. And now I can solve this, and it's going to give me the rate of car 1, because that's what we let x equal. So I end up with 6x plus 30 equals 240. So 6x equals 210. So x equals 210 divided by 6, which is 35. So how fast was each car traveling? Well, car 1 was traveling 35 miles per hour, and car 2 then was traveling 45 miles per hour. All right, so the second problem, I'm going to give you the opportunity to set up the table. It's a slightly different situation, but again, we're going to want to use the idea that rate times time equals distance. So that's going to help us solve each of these problems. All right, so at 1 p.m., a train traveling 60 miles per hour left Big City, heading to Old Town. And the distance between Big City and Old Town is 350 miles. At 3 p.m., all right, so 2 hours later, another train traveling 55 miles per hour left Old Town, headed towards Big City. At what time will the trains pass each other? If time is the thing I'm looking for, then I want to let x equal time. Now, I need to be careful about which time I'm talking about. Am I talking about the first train that left Big City, or am I talking about the second train which left Old Town? Because their time traveled is different. One train was traveling for longer than the other. So I'm going to say the time of train 1. Now, when I make my table, I need to make sure that train 1 has a time of x. All right, so train 1 has been traveling for x hours. Now, train 2 is traveling for less time because train 2 didn't leave until 3 p.m. So train 1 leaves at 1, train 2 leaves at 3. That means train 2 must have been traveling for 2 hours less than train 1, right? If the time for train 1 is x, the time for train 2 has to be x minus 2, 2 hours less than train 1. I can fill in the rates because I know how fast each train was going. So the first train was going 60 miles per hour, second train was going 55 miles per hour. What I don't know necessarily is what to do with my distances, so let me think about that for a second. I think, again, we're in a situation where the distance of train 1 plus the distance of train 2 has to add up to 350. So what is the distance that train 1 traveled? Well, rate times time equals distance, so train 1 traveled 60x miles, and train 2 traveled 55 minus 110, 55x minus 110 miles. And again, we can say, if I take the distance from train 1 plus the distance from train 2, that will give me 350 miles. And now I need to solve. So x equals 4, which means train 1 was traveling for 4 hours. So if train 1 left at 1 p.m., 4 hours later, then they must have passed at 5 p.m., right? 1 p.m. plus 4 is 5 p.m. All right, last one, and then practice problems. I probably won't do the practice problems. I'll just post my solutions to those. This video will get too long if I do another one of these. So the 2 practice problems you can do on your own and then check with my solutions on the Course Notes Hub. Okay, Joe drove to town, traveling 30 miles per hour. Okay, so we've got Joe's house and town. So Joe's going that way initially, traveling 30 miles per hour. He drove home at 50 miles per hour. So he drives to town and then he turns around and drives home, and he's doing these at different rates. Drives to town at 30 miles per hour, comes back at 50 miles per hour. The round trip took 4 hours total, so how long did it take for him to travel into town? Again, it's how long, so we're going to let x be time. And we're going to say into town. So let's set up a table based on everything we know. Well, we know that x is the time it took him to get into town. That's what we're setting our problem up as. And he traveled at 30 miles per hour to get into town. Took him an unknown amount of time to get back, but the trip took 4 total hours. So if the whole trip took 4 hours and the time to get there took x hours, so if this was time of x, then x plus something gets you to 4, right? So the total trip was 4, and some of that was x. Then if I take away the x, that will leave me with the time it took him to get back. So I'm going to say that my time for the return for Joe was the 4-hour total minus however long it took him to get into town. For example, if we find that it took him 1 hour to get into town, well, then it took him 3 hours to get back. If it took him 2 hours to get into town, then it took him 2 hours to get back, because the total has to add up to 4. And now we can figure out the distances. But we know that these distances have to end up being the same, because the distance to town is the same as the distance back from town. So when I do my 30x distance for going into town, and I do my 200 minus 50x coming back from town, what I know is that 30x, which is the distance traveled to get to town, has to be the same as 200 minus 50x, because that's the distance traveled coming back from town. And now I need to solve this equation. So I end up with 200 divided by 80, which I could reduce to 5 halves. 5 halves hours, or sometimes people like decimals, so we'll say 2.5 hours, or we could say 2 hours, and 0.5 hours is 30 minutes. So I'm going to go with that. 2 hours and 30 minutes. That's how long it took him to travel into town. And if we really cared about how long it took him to get back from town, we would just do 4 minus 2.5, and we'd get 1.5, and so it must have taken him an hour and a half to come back, which makes sense because he was traveling faster on the way back. All right. So these are the practice problems on the top 2 that you need to do today, just the first 2.